Hello and welcome to this video about our 2020 NeuroImage paper on trial-wise decoding from fMRI. So in order to understand this, we first need to have a look at basic fMRI data analysis, which often builds on, as you will probably know, the general linear model. So in the GLM, the measured signal from a single voxel is decomposed into variation coming from experimental conditions, the design matrix X, weighted by some regression coefficients, beta, plus some noise, which is assumed to come from a normal distribution with mean 0 and some covariance across scans. So in fMRI decoding, trial-wise response estimates for multivariate pattern analysis are often obtained by exchanging those conditions for trials, such that in the design matrix, each trial has its own HRF regressor. This is called the least squares all, or LSA method. And this approach is problematic because due to the very slow nature of the hemodynamic response and due to the fact that adjacent HRFs from adjacent trials are overlapping in time, this induces serial correlation into the trial-wise response amplitude and makes them more variable. For this reason, another approach has been proposed, the least squares separate, or LSS method. This approach uses a separate model for each trial, which has one HRF regressor for this trial and one HRF regressor for all other trials. Here's another comparison of these two approaches. And this second method is also called the Mumford approach and can be seen as the current state-of-the-art method for coming up with trial-wise parameter estimates in MVPA based on fMRI. So we have our standard GLM, which uses a condition-based design matrix, and the contributions of the individual conditions to the measured signal can be obtained using, for example, the weighted least squares solution. And we have the trial-wise GLM, which uses a different design matrix, here called XT, and the trial-wise responses can, again, be estimated using least squares. These two models can be related to each other as follows. So we can see the condition-based design matrix X as a linear combination of the trial-wise design matrix XT weighted by a trial-wise indicator matrix T, which we refer to as the transformation matrix. Essentially, this matrix T tells us which trial is belonging to which experimental condition. Here's a more complicated example in which we also have parametric modulators varying across trials. So given our definition of the transformation matrix, one can show that the trial-wise response estimates are following a new linear model using this transformation matrix as the design matrix, and another matrix U as the covariance matrix across trials. This matrix we call the uncorrelation matrix, and it can be obtained by multiplying the trial-wise design matrix with itself and weighting this using the inverse scan-by-scan covariance. Once again, here's a more complicated example in which we also have nuisance regressor. So we have the transformed general linear model, which is operating on the levels of individual trials, and which uses T as its design matrix and U as the covariance. How do we get from here to inverse transformed encoding model? First, we can take this univariate linear model and collect trial-wise response estimates from multiple voxels. For example, in a searchlight, a region of interest, or the whole brain. This gives us the multivariate transformed encoding model. If we then devise a strategy for inverting the model, we come up with the inverse transformed encoding model, which describes experimental design variable T in terms of trial-wise response estimates gamma hat. The key point here is that all these models are using the same temporal covariance matrix U, which can be incorporated into the estimation and thus accounts for trial-by-trial correlations. I want to briefly demonstrate this using a visual reconstruction analysis. So in this experiment, subjects were looking at such a circular stimulus. And this stimulus consisted of 48 individual sectors whose illumination intensities were randomly varying across trials. We first performed a model comparison analysis in order to identify voxels in V1, which are responsive to visual stimulation as such. And we then used these voxels in order to reconstruct the contrast levels in all the 48 sectors. Decoding accuracy was quantified via correlation coefficient between actual and reconstructed contrast levels. And in this way, we were able to show that the proposed item approach is much better than the naive LSA methodology, and it also outperforms the currently accepted LSS method. So with that, I want to say thank you. And if you want to know more, feel free to have a look at the paper, which is available open access. So thank you very much.